Today we are going to discuss a topic called as a thermal stresses under a subject solid mechanics. So first of all we will discuss, if you consider a bar having length L and temperature change subjected to temperature change delta T, then is there any stress induced in this bar? As we know, if the bar is subjected to change in temperature delta T, then as this bar is free at one end, there is change in length of the bar, and that change in length of the bar due to change in temperature is given by alpha L delta T. Now this terms alpha is coefficient of thermal expansion, length of the bar and change in temperature. But even though this bar is subjected to change in length, but always it is not subjected to change in stress, or we can say there is no stress induced always. I am talking about thermal stress. So we need to understand when there is thermal stress. So to understand this, let us consider these 2 points. If this natural expansion or contraction, means we know that if material is heated, it is subjected to expansion. If material is cool, then it is subjected to contraction. So this expansion or contraction is allowed to take place due to change in temperature is allowed, means it is allowed to take place, then there is no stress or strains are induced in that material. So very simple, if this expansion, natural expansion or contraction is allowed to take place, it is permitted, then there is no stress induced in a material, as well as there are no strains induced in that material. So when it will be induced? Very simple, if natural tendency of metal to expand or contract due to change in temperature is totally or partially prevented. So either it is totally prevented or partially prevented, then thermal stresses or strains are induced. Means here, instead of allowing this expansion, if I kept some support here, if I kept some restriction here, in this case what happened? This expansion is prevented. That expansion can be a totally prevented or it can be a partially prevented. So in this case there is thermal stress, and of course there will be a thermal strain. So this is very important point to understand, when there is thermal stress and when there is no thermal stress. Now as we know, if this temperature is raised, means if this material is heated, temperature is raised, then the stress induced in this bar will be a compressive stress, because this material will try to expand and we are going to restrict its expansion. So the stress induced will be a compression. So I written here it is, if the temperature is raised, then there will be compressive stress set, while if temperature is lower, then there will be a tensile stress set. So these 3 points we remember. When there is free expansion, there is no stress. If the expansion is partially or totally prevented, then there is stress induced, and if temperature is raised, then there will be a compressive stress, and if temperature is lower, then there will be a tensile stress. As we seen, stress is induced when the expansion of bar is either completely prevented or partially prevented. Now we will discuss a concept of a thermal strain. So it's very simple. In case of temperature change, the thermal strain is defined as change in length prevented to original length. So how much length of the bar or metal is prevented upon original length. Now let's understand this concept with the help of 2 cases, where case 1 is when change in length is totally prevented. Totally prevented means there is one bar fixed at both ends. So in this case there is no expansion is allowed, or while we can say total change in length is prevented. So to determine thermal strain here, what we seen, as we know, this bar, if there is no support here at this end, then this material will expand like this. And how much that material expansion will be? So if there is no if there is no support here, if this expansion is not prevented, then the change in length, we can say delta L is equal to, we seen earlier, it is formula is alpha L into delta t. So if there is no support here, then this bar is subjected to this much expansion. Let's say it is delta L. So this much expansion is prevented in this case. So if I want to find thermal strain, then I can write thermal strain, that is Et I am writing here, is equal to, we know that change in length prevented. So when how much length is prevented here? This much length is prevented. So it is equal to alpha L delta T upon original length. Original length of this bar is L. So this is your thermal strain. So from this we get, this L get cancelled, it is equal to alpha into delta T. But as we know, modulus of elasticity E is equal to sigma, that is thermal stress, upon thermal strain, and therefore thermal stress produced in this case is equal to E into this modulus of elasticity into thermal strain. How much thermal strain is? This much. Therefore thermal stress sigma is equal to E into alpha delta T. So this is your expression for thermal stress when expansion is completely or totally prevented. From this we can also determine a force produced here. Means actually when this bar is fixed at both ends, as there is restriction to expansion, this support will produce some force on this bar. And that force, let's say this force is F in this case. I am writing here this force F is produced. Why this force F is produced? This bar will try to expand, but as there is restriction, this support will produce some reaction on this bar. That's reaction force F is given by, as we know this thermal stress, so sigma is equal to F upon A. So by using this, once stress is known, area of the bar is known, we can determine force produced on the bar by this support, or you can say support reaction we can determine. So we seen here how to find thermal strain. It is total length prevented upon original length, that is alpha L delta T upon L, which is equal to alpha delta T, and by using modulus of elasticity equation we can determine thermal stress, that is sigma is equal to E into E of T, where E of T is equal to alpha delta T, and hence thermal stress equation is equal to E alpha delta T. Now we know that there is force produced here by this support on this bar as expansion is prevented, hence thermal stress is equal to force upon area. So we can determine this force using thermal stress and area values. Now let's say consider the case 2. In this case, how much expansion is prevented, that we need to find out, because strain is equal to expansion prevented upon original length. Original length is L. So this is known to you, but we don't know how much expansion prevented. Now let's say consider here there is some gap is given, and after that gap there is support. So up to this gap this material will expand freely, and then there is restriction to prevention. So assume that there is no support. So if there is no support, then this material will expand like this. This is free expansion, okay, and we know this free expansion, if there is no support, is equal to, yes, how much it is, delta L is equal to alpha L into delta T. But in this case, as support is there, this expansion is prevented. But how much it is prevented? We know that up to this support it will expand freely. So this much expansion is prevented. So your prevented expansion is this much. So how we can find this? It is nothing but this delta L minus gap, because up to gap it is allowed to expand. So this much is the prevented expansion. So we can write here length prevented, change in length prevented is nothing but total expansion allowed, the delta L minus this gap. So it is equal to alpha L delta T upon minus gap upon L. So this is your Et. In the similar way now we can determine stress, because we know that E is equal to sigma upon Et, and therefore sigma is equal to E into Et, okay. Sigma is equal to E into Et, and once you know this sigma, then we can find out sigma is equal to force upon area. So we can find this reaction force exerted by the support on this bar. So this is the case of thermal strain and stress produced in case 1 when partially prevented, when totally prevented, and case 2 when expansion is partially prevented.